Okay, the cardiac cycle. So we talked about the electrocardiogram yesterday and what's going on and where the electrical current is going. And we know that the heart has two pumps that work together. We have the left and right half because the left half is pumping the blood to where? The left half. The left ventricle is pumping the blood to the rest of the body, and the right just to the lungs. So they're working together. They contract at the same time, right? So when we are looking at blood pressure, really, we're looking at the contraction. Okay. The pressure.
I'm showing you how the heart works.
Mm-hmm. The pressure during contraction and the pressure during the relaxation, and that's called systole and diastole. Okay. When we look at blood pressures, and can't remember if we have this actually on there, but it's always when you see like 120 over 80, 120 is the systole pressure and the 80 would be the diastole pressure. Blood moves through the circulatory system from areas of high pressure to low pressure, and the contraction of the heart is what's providing that pressure. Okay, cardiac. So the first part of the cardiac cycle is the systole, and it begins at the completion of the QRS complex. QRS is that big peak, remember, in the electrocardiogram. The ventricular muscles start to contract, increasing the pressure inside the ventricles, and it causes the AV valves to close. Which is the beginning of the ventricular systole. Remember, systole is during contraction. The semilunar valves were closed and remain closed, so the volume of blood inside the ventricle does not change. That's why it's called period of isovolumic contraction. So the volume of blood does not change. There's no blood going into or out. Both valves are closed, but the ventricles are starting to contract. 120 to 130 milliliters of blood are in the ventricles, and that is left from the last diastole when the atria emptied into the ventricles. It is, I agree. So when it ejects the blood out of the ventricles, the pressure in the ventricle has increased to the point where it's greater than the pressure in the pulmonary trunk or the aorta. And that's when those semilunar valves will then open and the blood will rush into those arteries. The pressures in the two ventricles are different. Lot higher pressure in the left ventricle. Why do you think it has to have higher pressure? Get to the rest of the body, right? It just takes more pressure to get it there versus the right ventricle. After that first initial spurt of blood out of the heart, then the pressure will start to drop, and when that pressure drops enough, then the pressure outside of the heart is higher, and it will close those valves. So it's all based on the pressure. So diastole is relaxation. So we have a period of isovolumic relaxation, meaning the volume of blood inside the ventricles are not going to change. So it relaxes. Once the pressure inside the ventricle, it falls very rapidly. The pulmonary trunk aortic pressure is higher, which causes the semilunar valves to close. And the AV valves are also closed. Okay, when the ventricles are in systole, the atria we're filling with blood. So when the ventricles are contracting, that's when the atria is getting filled with blood. And when the atrial pressure gets above the ventricular pressure, then those AV valves open and the blood in the atrium just fills into the ventricles. And it just will flow into there just based on pressure, and then the atria will also contract. Here, during the depolarization of the SA node generates an action potential that spreads across the atria, which causes the atria to contract, which finishes off filling the ventricle. So it'll push any last remaining blood from the atria into the ventricle. So at rest, so when you are not doing any heavy exercising, you actually don't need the atria to contract. The blood just filling the ventricles from the change in pressure is enough blood for normal function. So you're getting enough blood. When you have higher oxygen needs, then you're going to need that atria, that extra blood. You just need all the blood you can get. And that just is that sound. Okay, so if we review back through, the ventricles, when they start to contract, the volume doesn't change. The valves are all closed until the pressure inside the ventricle gets higher than the aorta pulmonary trunk, and the blood leaves there while the blood is filling the atrium at the same time. When the ventricles start to relax, the pressure drops inside the ventricle, closes the valves, and once that is lower than the atrial pressure, then the blood just starts to fill the ventricle until the atria contracts, and it will fill the ventricle then with the rest of that little bit of blood. Okay, heart sounds that you hear when you listen to someone's heart, they're actually from the valves in your heart closing. So the first heart sound is a lub sound. They call it lub. When lub dub is how they describe the sounds. But so the first sound is the lub sound, and it's when the atrioventricles, so the AV valves and the surrounding fluid vibrations as the valves close at the beginning of ventricular systole. So when the valves between the atria and the ventricles close, that's the first sound. That's when the ventricles start to contract, and it's going to push the blood out the aorta and pulmonary trunk. The second heart sound is from when the ventricles start to relax and the semilunar valves close. So the first one is when the blood goes from the atrium into the ventricle, and when those valves close because the ventricles start to contract, you get that first sound, and then the blood gets pushed out the arteries through the semilunar valves when those semilunar valves close because the ventricles start to relax. That's the second sound. And occasionally you can hear a third heart sound, and that would be like a heart murmur or something like that. And that's caused by turbulent flow back into a ventricle. And it's usually detected near the first 1/3 of the diastole. Diastole was what? Then it's in below, so it's the lower pressure, it's when it's relaxing, right? When the ventricles are relaxing. If you think of systole, diastole, South Dakota, that's one way you can, kind of like numerator over denominator is North Dakota. So systole over diastole, South Dakota, you can remember which one's which, and if you know it's 120 over 80, 120 is a higher number, so that's when the ventricles are contracting. The 80 would be when they're relaxed. That's the way you can remember that. Okay, when you're looking at aortic pressure, so the pressure in the aorta right after it leaves the heart, there's a couple of different measurements you can take, but when the aortic semilunar valves, the pressure within the aorta increases slightly. And when you take your blood pressure in your arm, you're looking at aortic pressures really, not necessarily the pressure that's within the heart itself. You're looking at the pressure in the vessels, since which is called aortic pressures. And you can calculate the mean arterial pressure, which is the average blood pressure in the aorta, by using this equation. We really aren't going to use that equation. Nope. Where CO is the amount of blood pumped by the heart per minute. And CO is equal to the stroke volume and the heart rate. So the stroke volume is the amount of blood pumped each beat. Heart rate is the number of times per minute. So if you multiply those together, you can get the amount of blood pumped per minute. And then the cardiac reserve is the difference between the CO at rest and the maximum CO, because when you're at rest and not exercising, your heart doesn't have to pump as much blood. PR is the total resistance against which the blood must be pumped, and that could be based on any cholesterol, plaque, anything build up in your arteries that would cause resistance to that flow. We're going to go through that. Okay, regulation of the heart and the heart rate, it can be from intrinsic regulation, just results from normal functional characteristics, so not from the nervous system or hormonal. And it's just from the preload, because the preload is the amount of stretch on the ventricular wall. So as the ventricles start to fill with blood, they start to fill and stretch. And just like we looked at the reflex in your leg, as the muscles start to stretch, it'll cause them to contract and starts that ventricle. So it really has nothing to do with, it's more of a reflex. And then afterload is the pressure of the contracting ventricles must produce to overcome the pressure in the aorta. And so the heart is not as sensitive to this as it changes to the preload. Basically, it's changing the amount of pressure that the ventricles have to give based on the atrial or the aortic pressure that's in the aorta at the time. So that is saying. Okay, switch it. Okay. Extrinsic regulation involves the nervous system and hormonal control. So you can have parasympathetic stimulation, so it's supplied by the vagus nerves, which would decrease the heart rate. And then sympathetic stimulation, which is supplied by cardiac nerves. It innervates the SA and AV nodes, which increases the heart rate. And that could be, well, epinephrine and norepinephrine is released. It increases the heart rate, which causes increased cardiac input and increased force of contraction. So basically that is if your brain is sensing that you need more oxygen for something, it's going to actually stimulate an increase in heart rate. And that would be extrinsic regulation. Also hormonal control, like if you're in a fight or flight, some sort of situation, and your body would produce the hormones to change your heart rate and get you ready for that part. It also occurs in response to increased physical activity. So as you start running or exercising, it will release those hormones. So those are the extrinsic or external regulations. Internal regulations is just how your heart is monitoring stretch and pressures inside the heart and right outside. Okay, homeostasis. So homeostasis is bringing whatever, be it blood pressure or heart rate or anything back to a normal, how the body brings those set points back. So effective blood pressure, you have these baroreceptors in your vessels, so the receptors that are monitoring your blood pressure, and that information goes to the medulla oblongata, and it can regulate the heart rate and blood pressure that way. There's also receptors that are monitoring pH, carbon dioxide, and oxygen, and it can change the heart rate based on the levels of those ions or molecules.
So when you exercise.
Yep, like when you're exercising, you'd have more CO2 and less oxygen in your blood, so you're regulating that, and it's going to increase your heart rate then. Effect of extracellular ion concentration, so depending on the potassium levels, it can decrease the rate of the heart, increase or decrease the heart rate. And then body temperature is usually, as your body temperature increases, then your heart rate will increase, because remember, the first way to get rid of excess body heat is to have dilate the blood vessels at your skin. And so if your heart rate increases, you're getting more blood going past your skin, so it can radiate off that way. And then the opposite is true. When your body temperature decreases, your heart rate slows down to conserve that heat. That's just showing how those, you have all these receptors in all your vessels in the heart and where they go. Same idea. Going through how, what? Baroreceptor reflex, the cardio something, I don't even know what that word is, center increases the parasympathetic and decreases sympathetic stimulation of the heart. Heart rate and stroke volume decreases. Decreased heart rate and stroke volume decreases blood pressure. Yeah. Increased heart rate and stroke volume increases the blood pressure. Heart rate and stroke volume increases. Yeah. Here's the chemoreceptor reflexes. So looking at, it says increase in blood pH inhibits the cardioregulatory center. The cardioregulatory center increases the parasympathetic and decreases sympathetic stimulation. And the last part, effects of aging on the heart. So there's gradual changes in the heart functions, which is, the changes are very minor under resting conditions, but when you get to where you are exercising, your heart isn't able to keep up with the changes and the needs that it needed. Hypertrophy of the left ventricle, meaning you can get an enlarged heart. If you think of congestive heart failure, I don't know if any of your grandparents have that, but what happens is there's more fluid around the heart, it has to work harder, and so the ventricles get a little larger. The muscle and the heart walls get larger just because it has to work harder to go past that pressure. The maximum heart rate decreases. Increased tendency for valves to function abnormally and arrhythmias to occur. And my grandpa actually had to have a heart valve replaced, so they can do heart valve replacements now. Pretty sure his was the aortic semilunar valve they had to replace. I've heard that they can use pig valves, but I'm not for sure what his was. I don't know if they can do mechanical ones or if they have to use do heart surgery. And then increased oxygen consumption required to pump the same amount of blood.